Hello, isn't it amazing how you could wait so long for a mathematical video to come up and then when it does, 3 come along at once? Yeah, just because I've not been doing any for a while, you see, and as soon as I got into differentiation I thought I'd just do a few. Anyway, check out my other videos, product rule, quotient rule, chain rule, and another one on exponentials here, differentiating the natural logarithm. Okay, well, the result is that, okay, if I just do it in that order. So basically the result is if y equals natural log of x, then when you differentiate it, dy dx is equal to 1 over x. Okay. So that is essentially the rule. So what's this doing here? It's kind of an explanation as to why that works. Not a proof for you, I'm afraid. Look it up somewhere else if you want. I just want to demonstrate to you why it is 1 over x. Okay. Now, years and years ago, centuries ago, mathematicians were interested in something called quadrature, finding the area between a curve and the x-axis. And specifically, people were looking at reciprocal functions like y equals 1 over x. And in their research, they came across a rather interesting, wonderful actually, discovery. That is, when they were considering the area underneath the graph of y equals 1 over x, between the curve and the x-axis, they found that the area between the lines x equals 1 and x equals e was actually 1, which is rather fascinating. Okay. You've probably done some integral work already with areas under a curve, I'm hoping so. Of course, you know that's by the area under a curve you integrate, okay? So what that means is when we integrate 1 over x and substitute in the limits of x equals 1 and e, we should get an answer of 1. And of course, when you do the natural log of e, you get 1. Okay? And the natural log of 1, you get 0. So basically what mathematicians discovered was, I'm glossing over it a lot, okay? I'm just summing things up for you in a nutshell, okay? What mathematicians discovered was that the integral of 1 over x dx is equal to the natural logarithm of x plus c. When we talk about integration, don't forget the plus c, okay? Sorry for my writing, it's not very nice. In a previous video, my board pen just suddenly stopped working. No idea why. So in reverse, if the integral of 1 over x is natural log of x, the derivative of natural log of x must be 1 over x. Okay. You need to know both results, but I'm talking about differentiation primarily. Okay. So this is the result we need. Okay. Right, let's have a look at some examples with that then. So, 3 expressions, differentiate each of these. So the first one should be simple. As I've just said, when you differentiate natural log of x, you get 1 over x. That's it, that's the result you need to remember. What about this one? Well, of course, the way differentiation works is if you just multiply it by a constant value, like 2, you just multiply the derivative by 2. That's supposed to be 2 over x, 2 times 1 over x. This one here, this one always catches people out. What do you reckon it is? Well, the answer is actually just 1 over x. Maybe pause the video, take a moment to think about that if you thought it was something different. Why is it 1 over x? I can give you 2 reasons, okay? Reason number 1, using our laws of logarithms, you can rewrite natural log of 5x as natural log of 5 plus natural log of x. Remember how the log rules work? Multiply the 5 and x together to get the 5x. Now, when we differentiate these, that's just a number, a constant, so that would be 0. And then you differentiate natural log of x to get 1 over x. Okay, that's one reason. Another reason, using the chain rule. Okay, if we had y equals natural log of 5x, then we could say u is equal to the 5x, and of course du dx is equal to just 5. That would mean that y is equal to natural log of u. That's what 5x is. And dy du is equal to then 1 over u. Multiply them together, dy du times du dx, you're going to get 5 over u, which of course is the same as 5 over 5x. 5 over 5x, where the 5's cancel, you're left with 1 over x. Yeah, so 1 over x. Right? In general then, mathematicians like to say in general, kind of makes you feel like you're in the military, doesn't it? When you mentioned in general so many times. But there you go. Now, when we say in general, we mean when we use something like this. Okay? If y equals the natural log of kx, where k is some constant, reasonable constant. Remember, you can't take logs of 0 or negative values. So constant like 2, 3, 5, a simple number, okay, not a million. dy dx will be equal to 1 over x. And you can choose which result you prefer to use to show that. I prefer this, natural log of k plus natural log of x. Where the natural log of k is a constant, so just differentiate to get 1 over x. Okay. Other examples, this one here. Use the chain rule again for that. So dy dx is equal to, now the way the chain rule works with this is that when you differentiate a natural logarithm, the answer is going to be a fraction, and it will be 1 over the brackets 7x minus 2. The reason for that is, I've not finished the answer yet, if you were to write out the chain rule like this, you want whatever's in brackets to be u, so u equals 7x minus 2 in this case, so that gives us y equals natural log of u, and when we differentiate that, dy du is 1 over u. Hence y, always, when you're differentiating a natural logarithm, whatever's in brackets is going to end up in the power. And so it end up in the denominator there. Okay. Following this through then, du dx is going to be equal to 7. And when you multiply them together, that times that gives you 7 over u, which is 7 over 7x minus 2, which is 7. The way of doing it in your head is this, you just differentiate what's in the brackets. Okay. Remember the chain rule, if you had something like this, e to the 7x minus 2, you differentiate this and you get 7 e to the 7x minus 2. If you had 7x minus 2 to the power of 5, you do 5 times 7x minus 2 to the power of 4 times by derivative of this, which is 7. All works exactly the same way, doesn't it? Okay, here, just get used to seeing it in terms of natural logarithms now. Natural logarithm of this, differentiate the bracket 7, so 7 over 7x minus 2. Maybe before we do another one, I just ask you to consider another type of example. So let's just leave that by there for a moment. Try doing this question. What if y is equal to natural log of x squared plus 3x? Have a go at that one for me. So you get dy dx is equal to, that's going to be something over x squared plus 3x. Because differentiate a natural log, it's 1 over what's in the brackets. Then differentiate what's in the brackets, you get 2x plus 3. So it's 2x plus 3 over x squared plus 3x. Okay, that's that. Another example. Have we got this one? Yes, so I'm giving you a product rule question now with natural logarithms. So you'd have u is equal to x squared, v is equal to natural log 4x, and then you need to do du dx, which is 2x, and then you need to do dv dx. Remember what that is? Yeah, it's 1 over x. Remember that result. And then dy dx is equal to v du dx. So that multiplied by that, so 2x natural log 4x, and then plus, using the product rule, u dv dx, so x squared times 1 over x, that's just x. And we can't actually simplify it any further, can we? So that's just our answer. Nice and simple. Last example I have for you, quotient rule example. So you have to use u as the numerator, 4 natural log 3x, and v as the denominator, x minus 3. And then you'd have du dx is equal to, and then here, well, when you differentiate natural log 3x, you're just going to get 1 over x, so times by 4, 4 over x, and then dv dx is equal to 1. Nice and simple. So you get dy dx is equal to v du dx, so that times by that. Better write it out like this, I suppose. 4 over x, x minus 3. And then subtract, because using the quotient rule, u dv dx, so 1 times that, which is simple, 4 natural log 3x, all over v squared, which is x minus 3 squared. And then consider, is this a fraction in its simplest form? The answer is no, it's not. Okay, the reason it's not in its simplest form is because when we write a fraction, we don't have a fraction within a fraction. Okay, that's That's how you tell when it's not in the simplest form. When you've got a negative power in terms of x anywhere on top or the bottom, it's not in the simplest form. Because negative power effectively means it's a fraction within a fraction. Okay? Just as like surds on the denominator, we rationalise the denominator for that particular topic. We need to do something to get rid of this. The simplest thing to do, let's just change the colour, is multiply top and bottom by x. Okay? Show you clearly why I prefer to write the x's like this, so you don't confuse them with the multiplication symbol. Because, what if I wrote this? Useless. Okay? There you go. So anyone out there writing the x's like this? No. I'm joking, do what you want. Okay? I'm just showing you why I do it. Yeah, you can do it if you wish. Okay. Right, so multiply now the top by x, I'm going to get 4x minus 3. Subtract 4x natural log 3x. Yeah, don't forget to multiply all the terms by x. Yeah. All over x minus 3 squared. Okay. There's no point in factorising the top. There's only 4 is the only common factor there. There's no need. Okay, so there's no 4s on the bottom. There's nothing going to cancel. Okay, so that was that. Okay, hope you found that useful. Thank you for watching these videos. Okay, tune in again sometime. Bye bye.